All right, so our next talk, we're going to switch gears completely. I guess this has been kind of a potpourri session. And our next talk is by Sam Coward. Sam wears two hats. He is studying for a PhD at Imperial College London, but he is also working at Intel on hardware design. And I think what we're going to see here is a bit of an intersection between these. So Sam, go ahead.
Okay, so hopefully everyone can see slides and all that, so make some noise to come. But yeah, today we're going to be talking about how we came up with this new numerical hardware design methodology. This is very much methodology pitch, nothing really in practice. All the components exist, but we're sort of putting it together. But you know, as Pavel just introduced, I've got my Intel hat where I work on CPU design, and I've got my kind of researchy hat where I work on automatic data path optimization. And so what we deal with in graphics hardware is generating hardware that produces correct results, where correct is purely just, does it look okay on your screen? A lot of the time, a lot of our specs are much more flimsy than you have in CPU world. None of the IEEE stuff applies anymore. And so the reality is that our specifications are often, you know, natural language, no number formats. We generate non-bit accurate C models, and then we have to generate some really optimized RTL that maybe does something similar to what the C++ model does, but actually might do something entirely different. So the algorithm which we've been playing with as a group, so a numerical hardware group led by Theo Drain, is looking at this, basically generating approximate eigenvalues. And we've got a ton of different choices, like what components to use, what precision to use, what accuracies. And you know, we've been working on this for actually years. And so basically, when we look at this spectrum, you can do things at this top level of optimizing your algorithm, optimizing your architecture, all the way down to doing RTL level optimizations and bit level optimizations. And the reality of hardware design is that the pyramid is completely inverted with respect to how quickly we make changes. You know, bit level changes happen super fast. We change our logic synthesis algorithm, change the components there, and this happens really fast. But then the algorithmic changes happen way slower because it has so many massive.
My bad, I just accidentally muted you. I was trying to mute someone else.
No problem. But Bill says PhD in programming languages has been kind of pushing down from this top of the stack, whilst I've been pushing down up from the bottom of the stack. And so Theo basically said, can the two of us meet in the middle? And can we specify, simulate, implement, and optimize loads of different designs within a single day, looking at this full stack, rather than just looking at one component of it? And so basically, we have all these problems, you know, to actually specify this. We've got floats, fixed integers, precisions, and we also want to be able to execute. So this is kind of related to the work that has been done with the ARM specification about how we can do machine readable specs. And people are exploring that a lot these days. So maybe I'll quickly flash over FP Core as what we came up with as from Bill, bringing that into Intel as a good way to do these numerical specifications. And they're obviously executable with using some of the different techniques we've got. But what's really nice is you have all these precision annotations. So you've got these float annotations, as you can see down the bottom left here. And we have loads of different choices about how we can implement different components. So here we've got trying to implement A times B plus C plus D. And you know, there's loads of different ways in which we can implement this. And each of these different components that we could possibly build, we've got precision choices. So you can see the design space is massive, disaster, really hard to understand where to put your precision and how to actually tune these components, how to even select the components. Just more on the precision annotations, but hopefully this is familiar to a lot of people who've looked at FP Core before. So thankfully, we had already an FP Core simulator, such that we could go and chuck in a load of different designs using MPFR as a backend. We can actually go and figure out what is the result being produced by these things. From those results and from the simulator, we were actually able to go and build real application level visualizations. So this is just an ellipse plotter, because basically we're looking at how do we generate ellipses in this graphics algorithm. And you can see as we change the proposed precision, so we have this blue ellipse representing our sort of current implementation. As we increase the precision, we do get closer to that green ellipse, the golden reference model. So that's kind of exactly what we wanted. But also we have a ton of choices. Well, we have all these precision choices. So what this allows us to do is put these precision annotations in. and run a different ton of simulations to actually generate how is this the correctness in proportion to maybe some notion of hardware cost. And like all good academics, we chose the sum of all precisions to be, so this is basically the total number of bits to be our ridiculous hardware cost metric. But actually you can see it correlates quite nicely. You know, as you increase precision, sure, it does look like we're getting more accurate. One thing we did notice is that we can detect numerical instability using these techniques, like inherent numerical stability, because even as you're adding hundreds of extra bits, we can see that. So this actually goes up to 16 bits of total output, and we can never get past 10 bits of output precision. Even as we're adding hundreds of extra bits, we get no extra precision beyond 10 bits. We can't get to a full 16 bits. So what we actually detected that was that, you know, there's inherent numerical instability in this algorithm. And so we were able to refine that algorithm and generate this right-hand plot where we do get this nice frontier emerging. I think this is of the order of 100,000 points. You can see the frontier emerges pretty quickly as we simulate these different points. So having done all that, we built this compiler, Bill built this compiler with Brett that looked at how can we take FPCore and generate bit accurate C++ models, because this is what we actually need to go and put into our simulation frameworks and into all of our downstream tools, all sorts of things. So you'll see we get some horrible templatized C++. So we take this FPCore on the left and generate some quite scary looking C++, but it targets this library that Bill and Brett have built up, that then you can map these arbitrary precision computations into arbitrary precision C++. In addition to that, they actually worked on generating ASL, which is an architecture specification language, which is related to or being brought over by Alistair Reed as similar to the ARM specification language. And also we can look at how can we generate multiple different outputs. So having built the compiler, it's relatively easy to then go and map that into lots of different target outputs. But this is where we kind of see a problem from a hardware perspective. We have this sort of infinitely precise specification where we can choose any arbitrary precisions. And then we need to generate some reasonable bit widths for our C++ model. And then we need to generate actually some optimized hardware where, you know, we're not using reasonable bit widths. We want to use the smallest possible bit widths in our final generated hardware because bits correspond to area and delay in general. And so this is where we think we can use things like HLS to actually generate at least some reasonable performance hardware to give us some estimates early on in the feedback in the design cycle. We can get some estimates of how much area, how many cycles this thing is going to cost. But what the problem is that HLS, at least in the graphics domains, doesn't really achieve the desired power, performance, and area that we require if we're going to go and implement this stuff. And so this is where some of my work has come into this, which is about how do we take and optimize numerical hardware designs. And so, as you can see, we've taken this thing on the left, which is a very kind of simple floating point adder code where you're doing some addition, you're doing some renormalization, and then you're just truncating the output. And you can see going from the left to the right, the number of bits we're using drops from like 277 down to 25. And basically, we decided that competitive data path design is pretty much doing some value range analysis and rewriting and constraints. And so that's where we built this rover tool that basically takes in some initial RTL, does value range analysis and eGraph rewriting, which I won't necessarily spend too much time on today. But it's able to go and explore this massive design space of equivalent implementations of hardware designs, and then extract from that design space it's explored different area delay trade-offs within the single hardware. It also produces a formal verification flow where we can generate a load of intermediate steps, basically like a translation validation technique you'll find in compiler design. And it kind of works, which is nice. So we see that it can take a simple floating point add-off, floating point subtractor design, and generate something that is 33% faster and 41% smaller. So in a relatively large amount of time, because this is more towards super optimization, but in general, in hardware world, we're willing to spend a bit more time on super optimization. So this is what Theo believes to be a one-day operation. So one person writing your FPCore, at the front end, where we're generating some application level visibilities, doing your precision tuning using the simulation method we described, generating a C++ model that can then be fed into your simulation tools or into other flows down the line. That can also be shared with the system C. And finally, passing it on to Rover to generate your optimized hardware. What's nice about this flow is that you're getting this feedback at each stage of your design process, rather than, some architect giving us some specification all the way down to the hardware designers, where there's no real interaction going on. We don't really have any idea of how this is going to look. It's a bit of difficult to schedule, difficult to plan. One thing that really doesn't exist at all at the moment is this interaction between IFP and Rover. So what should that passing of information be? Classic compiler stuff. How do you best communicate your intent from the left-hand side of this graph all the way over to the right-hand side in hardware design language? So that is left open. Maybe there should be some shared IR. Maybe MLIR has some insights for us there. So yeah, thank you very much. Any questions?
Very cool, Sam. Very cool work. Just before I get to anyone else's questions, since I can do that, how many different circuits or whatever have formulas have you used this kind of pipeline on? At least if you can share. Do you have some estimate? Is it like a couple? This is a work in progress, or is this being used pretty widely?
We're basically doing this for the first time in this coming 6 months or something, or 3 months. So we're midway through the process, probably somewhere at the halfway stage of doing this for that graphics algorithm we described at the start.
Cool. So I see there's a question from Zach. You want to take the first one, other than mine?
Yeah, sure. Okay, so Sam, I guess there's a couple of things I was curious about. One is there's different cost functions being used in different phases. So the precision tuning cost function uses this kind of bit cost metric, and the Rover optimization is using more PPA. Presumably there's some relationship or interaction between these cost functions. I don't know, is that explored? Do you have any advice for when you have this sort of multi-phase pipeline, how to make the cost functions play nice together?
Definitely not explored. Only what we can say is that when Bill looked at how does this dummy silly cost of adding up all the bits compare to the metrics you were generating from high-level synthesis, actually they tallied up relatively closely. The same trends were emerging. Sure, you maybe weren't making an optimal choice, but you weren't making necessarily a disastrous choice, I think is what we can suggest. But of course, there should be actually backward arrows going on in this flow, right? If you want to go all the way back, actually the hardware, really this is a one-way line, but we should have these backward arrows telling us, from the hardware design perspective, actually making this precision choice here prevented us from doing optimization X, Y, Z. Maybe if we increase the precision, we can actually do further optimization. So there's a trade-off between squeezing your bit width down as much as you possibly can, and actually then preventing your compiler down the line doing a load of stuff.
Yeah.
But because we've got this full flow, that really we can have that backward arrow.
I mean, I guess also with those intermediate visualizations, you're still enabling people to do that, right? When this kind of gets to the other question I had, which is how important is it for each of these phases to be predictable in terms of being a automagic search versus maybe a compilation where I know how to control what comes out the next stage of the pipeline by tweaking what I put in.
I mean, from a user perspective, you want to know. So one of the things we really suffer from in logic synthesis, I made my design better. I removed some gates, but actually the generated circuit got worse, and that's the most upsetting thing for a designer. So we always want to have, if some notion of the designer clearly thinks this is better, that should feed through into what we see in our visualizations. If that visualization gets better, then we should be seeing that accuracy improve. So I think it's tallying that up, which is a bit of a vague answer, but yes. I think monolithicity is hard because there's also a lot of other tools going on in the flow here, which we don't have control over. So the HLS tools are all closed source, the logic synthesis tools are all closed source. So maintaining that relationship through is not trivial.
Right.
Okay, so there are more questions in the Slack, both from me and others. But I think we should move on to the last talk